So how does the interaction between Plutus and staking work? We have talked about script purposes. If you recall the script context that our Plutus scripts always receive as one of the arguments, contains a field of type script purpose. And during this lecture so far, we have only looked at the first two purposes. The arguably most important one is spending TX outref. So when we are spending a UTXO sitting at a script address, this UTXO is identified by its TX out reference, then the corresponding Plutus script is executed and it receives the datum of the UTXO we want to spend, the redeemer, and the script context. And then we can put arbitrary logic in the script to determine whether spending this UTXO is valid. Then we had the minting script purpose, which is for minting and burning native tokens. So whenever a transaction mints or burns a token, then the minting script corresponding to the currency symbol of the token is executed. And again, we can use arbitrary logic. The script receives a redeemer and the script context, and we can determine whether minting or burning for this transaction is valid or not. But we haven't talked about rewarding and certifying it, and those two are related to Plutus and staking. So as I briefly mentioned before, instead of using a public-private key pair to create a stake address, we can instead use a Plutus script. And then the hash of that Plutus script will give a stake address, a script stake address. And where, as we saw in the previous example, if I want to withdraw my rewards, for example, for a normal stake address, I have to, as witness that I'm allowed to do that, provide the signing key for this stake address. So if I use a script stake address, then instead the corresponding script will be executed. It will receive the redeemer and the script context. And again, I can use arbitrary logic to determine whether this transaction is allowed to actually withdraw those rewards. Similarly, certifying decert. So there are various certifications that I can attach to a transaction. In particular, important for staking are registration, delegation, and deregistration certificates. So if I newly create a stake address, I first have to register it by creating a transaction that contains a registration certificate for this stake address. Then if I want to delegate to a pool or change an existing validation, I have to use a transaction that contains a delegation certificate, and that certificate then contains the pool I want to delegate to. And finally, I can also unregister a stake address again and get the original deposit back that I had to pay when I registered the stake address. So for those, then, if I do a delegation, for example, then again the corresponding script will be executed and can contain arbitrary logic to determine whether this delegation, for example, is legal or not. So I want to concentrate on the rewarding purpose in this lecture. So if we look at the TX info field, we have seen examples of various of the fields contained in it, like the inputs, the outputs, talked about the minted value, we talked about the valid range that allows us to argue about time, the signatures, but we haven't looked at these two fields here. So here we have a field with all the certificates that are attached to the transaction. And now relevant for this lecture, we have a list of pairs containing of staking credentials and integers for withdrawals. So each pair corresponds to the withdrawal of rewards from the stake address given by the staking credential. So the staking credential corresponds to our staking address given by a Plutus script. And the integer is the amount of Loveless we are withdrawing. So whenever we withdraw rewards from script staking address, then the corresponding Plutus script will be executed and will receive this credential as argument in the script purpose. I created module week 10.staking to provide an example, and it's probably not a very useful or realistic example. So the idea is that withdrawals are only allowed if at least half of the withdrawn rewards goes to a previously specified address. So anybody can withdraw rewards from the staking address, but half of the rewards always have to go to a previously specified address. So let's look how we can do this. So it's a parameterized contract. So the first argument is the parameter, the address that will always receive half. Next comes the redeemer. So I just use unit. And then as always for Pluto scripts, the script context. And the result is a Boolean indicating whether this is okay or not. So I call the address address, unit is always unit, context CTX, and I do a case distinction on the script context purpose, the purpose of the context. So if it's certifying, I just say true. So that means I allow arbitrary delegation and deregistration. For minting and spending, it's false. But the interesting case is rewarding. So rewarding credential. And here I must check that what I said is satisfied. So this specified address receives at least half of the rewards. So if not, then I log this error, I trace this error, insufficient reward sharing. And I check that this here will be the amount I'm withdrawing, the total rewards. And twice of what I pay to the specified address must be greater or equal to the total rewards, which the other way around means that paid to address is at least half of the total amount. So this is the logic, and now I just have to compute the various things. So as often before, I define info, which is the TX info field sitting in the script context. Now to get the amount, the total reward amount, given the staking credentials, and those I receive here in the purpose, and then I can use them as an argument here. So giving the staking credentials, I have this helper function that receives a list of pairs of staking credentials and integers. And I call that with the field we just looked at in the txinfo, this txinfo WDRL field, which contains such pairs. So if it's the empty list, then I didn't find the correct withdrawal and I trace an error. And if it's not empty, so there is at least one pair with some credential and some amount, I check whether the credential is the one I'm interested in, the one I'm validating right now. And if so, then I have found my amount. So I return that. And otherwise, I recursively look at the tail of the list. So this amount function will give me the number of withdrawn Loveless. And the paid to address is supposed to be the total number of Loveless paid to the specified address. So I use a fold left, which is defined in the Plutus prelude. It starts with an accumulator value of 0, and the idea is I just loop over all the outputs, and if they go to this address, I extract the amount of Loveless contained in that output and add it to the accumulator. So this here is the list of all outputs. And this function now defines how to accumulate. So first argument is the previous value of the accumulator, then the output I'm focusing in now, and the updated value of the accumulator. So I call this previous value n and the output o. I look at the address of that output, and if it's the given address, then I add to my old accumulator the number of Loveless contained in the value of this output, and otherwise I just keep the value of the old accumulator. So the effect will be I sum up all the Loveless values contained in all the outputs that go to the specified address. And that's already it. That's the logic of my validator. Now I have to compile it to Plutus core script. And this is similar to what we have seen before. So you notice that this is a typed script. So I'm not using built-in data. I'm using Haskell types unit and script context. And we saw how to handle that for spending purposes and for minting purposes. For staking, it's for whatever reason done a bit differently. So if you look at module ledger.type.scripts, there's this function wrap state validator. And provided we have a redeemer type that can be converted to built-in data, and we have something of this type, which fits well to what we have defined in the example, so redeemer script context going to bool, then this wrap stake validator converts it into a function of type wrapped stake validator type, which is built-in data to unit. So using that, given an address, I can use the function I just defined, apply the address to it, then I get something of this type, unit to script context to bool, which is exactly what I can pass to wrap stake validator. So the result of applying wrap stake validator to that is of type built-in data to unit. So the whole thing together with the address is then of type address to built-in data to unit. I compile this and I lift the given address and apply it to this compiled Plutus script. So then I end up with something of the right type, namely built-in data to unit. So this is very similar to what we did with typed validators for spending or minting. It's just a little bit different how to apply this wrap stake validator. And out comes a stake validator. And that's all we need. So it's refreshingly short, actually. Now, of course, to use this in the Cardano CLI, we have to serialize the script to disk. And this is very similar to what I did before. So this write stake validator, I basically just copied the function from week 3, where I showed the same for a spending validator for normal Plutus spending script. It's almost exactly the same. So I first apply stake validator to the address to get my stake validator. And now I have to unwrap that to get to the underlying script, and there's a function called get stake validator. So that was different for spending script, but this was the only difference. The rest of this pipeline here is exactly the same that we used before. So this will write the validator to disk given the address. And in order to conveniently do that, I also need the ability to take a address in the format that the CLI uses and convert it to a Plutus address. And we had the same problem before in week 6. So I basically just copy pasted the code we had there. So these two helper functions, credential ledger to Plutus and stake reference ledger to Plutus, and then this try read address function. So that's just copied from week 6. So given a string, it passes that into a Plutus address or tries to pass it into a Plutus address. Finally, I defined an executable, which receives two command line parameters, a file name and an address. So it passes the command line, passes these two parameters, then passes the address, the Plutus address from this given string, and then it uses this write stake validator with the provided file and the passed address to compute the stake validator parameterized by this address and serialize it to this file. And this is already all the Haskell or Plutus code that we need. So now we can try this out in the private testnet.